Okay, so let's recap where we were. So in the first video, we kind of explained some of the deficiencies of the rational numbers. And in the previous two videos, videos 2 and 3, we kind of explored some of the properties of the rational numbers and made them more concrete. And we explored both the algebraic and the order properties. Today, we will combine these properties to view the rational numbers as what we call an ordered field. So not only will we consider the algebraic and order properties in isolation, we will consider them together now. And next time we're going to construct and explore the real numbers, although we will actually state the existence theorem for the real numbers today. Okay, so let's get started. And this section will be called ordered fields, of course. Okay, and it's definition 10. Okay, let's just jump right into it. So, an ordered field is, okay, well, let's kind of think through this briefly. So, we need a set F, will be like our underlying set that we want to turn into an ordered field. And we need two operations, addition and multiplication, of course, but we also need an order. So actually we need four things here. So it's an ordered quadruple, an ordered four tuple maybe, four tuple, it's an ordered quadruple, F plus times, and then less than, such that, so F plus dot is a field, and less than is an order on F. I almost wrote S there. Okay. However, this isn't enough, because we need to think about how. So right now we have these two distinct components. F is a field and F is an ordered set. But we should be careful, because we want the ordered set to behave in certain ways. We want the order to interact with the operations of addition and multiplication in specific ways that make sense to us. So we make two additional axioms, and we'll call them OF1 and OF2 for ordered field 1 and ordered field 2. OF1, if x is positive and y is smaller than z, then, it should be x plus y is less than x plus z. Actually, x doesn't need to be positive. I don't know why I wrote that. That was really stupid of me. And the second one is if x and y belong to F, and x and y are both positive, then so is their product. Okay, so that should be making sense. And I'm going to just state a few facts. Okay. The first one is simply that And this shouldn't be surprising. And also note that I didn't write q plus dot less than. We really mean that, but again, like it's like in the previous videos, we don't want to write out all of that. It gets so tedious. So we don't do that. What else? So if x is bigger than 0, call x positive. If x is less than 0, call x negative. Okay, I guess this is more of like a definitions than fact, but that's fine. Okay, so Q is an ordered field. I'm not going to prove that, but it's true. Okay, and just to give like some practice, working with the axioms, let's prove a lemma. Okay, so let F be an ordered field. Okay, so if x is bigger than 0, then what we have, negative x is less than 0, and vice versa. And if x is positive and y is smaller than z, then xy is less than xz. If x is negative and y is smaller than z, well, then it reverses the sign from above. So xy is less than xz, or xy is bigger than xz, I'm sorry. And if x is non-zero, then x squared is bigger than 0. In particular, 1 is bigger than 0. Isn't that funny that we feel compelled to prove that? And the sixth one, if 0 is less than x is less than y, then we have this inequality. Okay, and let's prove these. I'm trying to alternate colors because I think it improves the readability. Okay, so say x is bigger than 0. Well, what we have is that 0 equals minus x plus x, of course. And that is going to be bigger than minus x plus 0 by OF1. And, okay, but that's just negative x. And then by the transitivity, we really have, or equality and our order are transitive. So 0 is bigger than negative x, i.e. negative x is less than 0. Okay. And if x is smaller than 0, well, then negative x is bigger than 0 by almost identical reasoning. You can prove it yourself if you want an exercise, but I won't write it here. Okay. Say x is bigger than 0 and y is less than z. Okay, and we want to show that xy is less than xz. So y is less than z implies that, what does it imply? Well, it implies that z minus y is bigger than y minus y, which is just 0, of course. So now we have z minus y is bigger than 0, and x is bigger than 0. Okay, so now we can use OF2 to tell that their product is bigger than 0. So xz minus xy is bigger than 0. And then we can just add over xz is bigger than xy. Okay, and that proves B. And let's prove C. Say x is smaller than 0. And still that y is less than z. Then what we have, well, what we can do, we can write this funny looking thing. And let's think about this. So this equals negative x times z minus y. Okay. But remember, x is smaller than 0, x is negative, so negative x is positive. And y is less than z, so z minus y is also positive. So this whole thing should be positive. Okay, so negative x times y, or z minus y, is positive. But that proves that if we take the negative of this, we get x times z minus y is negative. And then we can expand xz minus xy is negative. So xz is less than xy. Okay, and that proves C. Okay, and if x is non-zero, then we want to show that x squared is positive. In this case, if x is non-zero, either x has to be positive or x is negative by trichotomy. Okay, so in the first case, x squared, which is x times x, is just the product of two positive numbers, and we're done by OF2. Okay, in the latter case, well, x smaller than 0 implies that negative x bigger than 0. But we just showed that if a number is positive, then its square is positive, so negative x squared should be positive. Okay, but negative x squared is just x squared. So x squared equals negative x squared is bigger than 0, and we win. Okay. We want to show that 1 is bigger than 0. Well, 1 equals 1 squared, which is bigger than 0 by d. Okay, so that was a one-liner. Okay, and now say 0 is less than x is less than y. What we want to do, let's note the following. So y times 1 over y is 1. X times 1 over x is 1. Okay. And what these show in particular is that 1 over y is bigger than 0, and 1 over x is bigger than 0. Okay? So now what we can do so we have 0 is less than x is less than y. So 0 times 1 over x times 1 over y is smaller than x times 1 over x times 1 over y, which is smaller than y times 1 over x times 1 over y. Okay, and this is going to be 0 is less than 1 times 1 over y, which is less than 1 times 1 over x. Okay, but then 0 is less than 1 over y, which is less than 1 over x. Okay? And that proves this whole lemma. I believe it was lemma 11. Let me check. Yeah, lemma 11. Okay, so we've proven lemma 11. Okay, and, just like I've mentioned before, we could just go on and prove facts about ordered fields all day, but that's not really our purpose. I really just wanted to illustrate the axioms and how to use them. So we'll mostly use basic properties of ordered fields freely from now on. And again, the cool thing is that Q is an ordered field, so all of these properties apply there, for instance. Okay, I think we've beaten around the bush long enough. I'm going to introduce our first major theorem. Theorem 12. And existence, uniqueness. For the real numbers. Okay, and this theorem, there exists a complete ordered field, by which we just mean an ordered field that is complete in the sense that we described in the previous lesson. R, which contains Q, as a subfield. R is unique up to isomorphism. Okay, so we've stated this theorem. So basically, it's an existence and uniqueness theorem. So, in the way we would prove this theorem, there's actually a lot of ways you can prove it. But the way we will do it is we will prove it via Dedekind cuts. And we'll do that in the next video. I don't want to prove it in this video because I want the video where we prove it to be a self-contained video so that you could skip it if you wanted without loss of continuity. Because it'll be pretty dry, but it would also be maybe considered more of like a supplementary video in the sense that you could really watch every other video and understand it perfectly without watching that video. So it's really like a bonus topic. That being said, I think it's a cool topic to look at. And if you haven't heard of like what it means to be like isomorphic before, let me give a quick example. Not related to this, but just kind of just like as an example to understand what it means. So think of an isomorphism as a structure-preserving bijection. Between two sets with some given structure. So, for example, we could have like group isomorphisms. Ring isomorphisms. Poset isomorphisms. If I'm throwing all these terms and you don't know what they mean, that's fine. But the point is, like, if you have a structure, so basically, if two groups are isomorphic, that means that there's a structure-preserving bijection between them. So basically, they have the same size, and they have the same structure. So even if they look different, they act the same, and we could really view them as the same group. And for an even more like naive, like perspective on this, say we have like the natural numbers, and 1, 2, 3, 4, 5. Okay. And, we have like the usual structure of like addition and multiplication on these. What if I introduced a new set called M, bold-faced M, right? Okay. But the elements of this set were Roman numerals. Okay. Are these different sets? Yeah, I mean, ostensibly they look different. But, so M and N are not the same set. But they do have the same structure. Right, and we can come up with a really obvious structure-preserving map. 1, 2, 3, 4, 5. Well, yeah, we can come up with a map that maps 1 to Roman numeral 1, 2 to Roman numeral 2, 3, 4, 5, etc. And moreover, this map's clearly a bijection, but it's also structure preserving, right? So if, say, we call our map phi, Well, then, so 1 plus 2 equals 3, right? And Roman numeral 1 plus Roman numeral 2 equals Roman numeral 3. So what we actually have is that phi of 1 plus phi of 2 equals Roman numeral 1 plus Roman numeral 2, which is Roman numeral 3. But also, if we think about it, phi of 1 plus 2 equals, well, that's phi of 3, which is 3. So in particular, phi of 1 plus phi of 2 equals phi of 1 plus 2. So basically, like, this is a structure-preserving map. And that's kind of what we're getting at. So if you haven't seen this, or if that confused you, don't worry too much about it. That was just like a cute little example. But in the next video, we actually will prove this, Theorem 12. And that's kind of what it means for the isomorphism part. We won't really harp on it later, so don't worry too much about it. But if that's an interesting topic, a course in algebra or even like category theory might be interesting. Okay, so until the next video.